Okay, you can type if you like in the chat. Okay, one of you have suggested we can carry multiple signals over single channel. Yes, you can compose what we call composite signal by combining individual signals and then put all those into the channel for transportation. Very correct. That's one need we may have. One other Karyavasam has suggested to have antenna size physically possible. Yes, that is another valid reason. Because for very low frequencies, the lambda will be large. Antennas are of like lambda by 2, lambda by 4, like related to the lambda. So antennas will be too high, too large. Power requirement will be too high if we try to transmit at lower frequencies. Any other? Both of you are correct. Filtering. Right? Sometimes it's easy to do the sharp filtering at the higher frequencies, because at lower frequencies, when we make filters using discrete components, the roll off or the cutoff will not be that sharp. Right? So to get rid of the noise, get rid of the interference, keeping the signal pure, it's easier at the higher frequencies like carrier. Right? So let's put it into a summary. As you said, antennas need to be of practical size. And also you said carry multiple signals over a single channel. You called it multiplexing in the previous semester. Like this. So you may need modulation to shift the baseband of individual signals to different frequencies so that you can put everything together into one composite multiplexed signal. Another factor is ease of amplification. At the baseband frequencies, amplification is very costly, and you need higher power. But in carrier frequencies, you can reduce the power level. At a lower power level, it can go a long way, can go a long distance. For example, if you take an audio signal, think of a music show, and in the open space like a ground, people put loudspeakers, right? And you put high power amplifiers like 500 watt, 200 watt kind of a power amplifier, and then put the output to the speaker. The speaker is like an antenna for audio, and you know it cannot go very far, right, with that power. But when you modulate audio onto a frequency, high frequency, few milliwatts may be enough to send over many kilometers. Amplification is also easier here because audio kind of amplifiers they are fairly big. Transformers as well as power amps, they are big in size. But as the frequency increase, the component sizes and the equipment sizes all decrease. Therefore, that amplification process becomes easier. Then removal of noise and distortion, because sharp filtering is possible at higher frequencies. Okay, so these are the reasons why we need modulation, and we are always in search of better or more efficient modulation techniques. AM has been one of the oldest, one of the oldest modulations. However, it was spaced out in like applications like broadcasting. We don't use AM anymore. We shut down all AM transmitters some time back. But few years back, a few years ahead from now on, AM is coming again in a different form called QAM, even for broadcasting. That's why we are studying the principle still, although in some application areas AM has been removed. The principle remains, and that principle may come back again in digital form to modulate digital signals in the form of quaternary AM like that. So that's why this principle is important for us. Let's define this word modulation. One definition could be, it is the process whereby selected property of the carrier wave, it could be amplitude, selected property could be amplitude, could be frequency, could be phase, and that selected property is varied according to or in proportion to the variations of the baseband signal amplitude, right? So depending on the selected property of the carrier, we may decide to modulate the amplitude of the carrier. Then we call it amplitude modulated signal. If we modulate the frequency of the carrier, we call it frequency modulated signal. We modulate the pace of the carrier, we call it pace modulated signal. One question I have is, does not attenuation be higher in higher frequencies? Well, free space attenuation wise, yes. Free space loss. Free space loss is some constant plus 20 log F plus 20 log D, right? So therefore, higher the frequency, free space loss will be higher. Free space loss is what we call spreading loss. Right? But spreading loss is only one of the losses. There is absorption loss. There is another loss in the medium which is serious, which is called the absorption loss by various particles like atoms. So depending on the medium, the absorption loss can be very different, especially at low frequencies like audio. When you try to transmit using a speaker, spreading loss is proportional to the frequency. However, the absorption loss is very high for all audio frequencies. Therefore, you find that to overcome the air barrier, like you use air in order to transmit audio because it's not RF, it's acoustic then. In acoustic signal like this, what I mean by low frequency signal here is the audio acoustic signal, then overcoming the acoustic impedance is significant, and you need a lot of amplification to send amplified audio over air without modulation. I mean, without modulation over the air, it's very difficult. So you need very large equipment also there. Okay, so your idea is correct. Proportional to the frequency, that part is called the free space loss. Right? Okay, modulating the carrier now. We already identified the property could be property we choose to put on our information could be the amplitude of the carrier, resulting in AM modulation. If it is frequency of the carrier, resulting in FM modulation. If you have chosen the pace of the carrier, it will result in a signal called PM, phase modulated signal. All these three belong to what we call CW modulation, continuous wave modulation. They are not digital modulations. They are called CW modulation techniques. Then, when you modulate the amplitude of the carrier, there are various options available. For example, using that principle of AM, there are certain derivatives you can take out from AM signal. One called double sideband suppressed carrier modulation. Another one called single sideband modulation. Another one called vestigial sideband modulation. All these are based on the AM principle, but slight variations. Because they are not directly AM, they are variations of AM. They are called AM derivatives. We will have a look at the derivatives also. Then we will revise what you learned on amplitude modulation. This is the idea. The amplitude of the carrier wave is varied according to modulating signal waveform. Let's do a small amount of analysis on this. Make a very simple assumption that your modulating signal or the message signal is just a sine wave. Practically, it is not. However, we will make an assumption like that for simplicity. This is just to start with, right? So, because I am assuming a single tone modulation, single tone means single frequency modulation. The tone frequency I will assume as modulating signal frequency. This is modulating signal amplitude AM. And this is, I'm assuming that this is my information signal that needs to be transmitted to a distant place. So, and I have to load it onto the carrier. At the moment, when you take the carrier wave, this is a constant. Okay. However, after the message signal is modulated, this will not be a constant anymore. Okay. This will be a variable according to modulating signal. Modulating signal, let me call it xt. So new amplitude after modulation should be the original amplitude AC plus your modulating signal. So that xt has to be added onto the original amplitude. Now the information content is imparted to the amplitude of the carrier. So which we can rearrange as now. Overall equation now will be this cos 25 CT. We will just copy here. This part is our new amplitude, which is the original amplitude plus xt information. And that will look like this when you look at the time domain. Amplitude is no more constant. You can see it follows that pattern of our modulating signal like this. And the mirror image is there on the other side. So that part we call the envelope. Because it looks like envelope of the variation. Right? So equation of the envelope is what we discussed earlier. Equation of the envelope is this. Envelope is that just this outer level, right? Outer variation. This portion. Right. What are the values, actual values? This will be the summation of original amplitude plus the modulating signal amplitude now. So it was AC plus AM, and this minimum will be AC minus AM, and the middle will be original amplitude AC, and their mirror images are there on the other side, like this. Okay. So these are the levels, different levels. This is minimum, maximum. And we define depth of modulation, or initially we will define modulation index like this. Let's call it mu. I hope you use the same notation in the previous semester, but some books will call this simple m. Some books will call this simple m, but I will be using mu. And I hope you use the same notation in the previous semester. The amplitude of modulating signal divided by amplitude of the carrier. So amplitude ratio between the modulating signal and the carrier is what we call modulation index. Shall we introduce that also into the equation, taking amplitude of the carrier out of this bracket? We can write it like this. And now we have this portion as our mu. So replace that with mu. This is another format of the AM equation. In fact, what we are writing is called singleton AM equation. Singleton amplitude modulated signal, because we assume that our modulating signal is a single tone, right? So in terms of mu, these levels are peak level will be 1 plus mu times amplitude of the carrier. Minimum is 1 minus mu times amplitude of the carrier. And this is the mid level, the carrier original amplitude. These are the negative side values of the same. We can break this or decompose this into its constituent frequency components so that we can plot the spectrum, right? How do we do that? Just expand using trigonometry. Just remove the brackets by multiplying, right? So that you will end up with this, and you can expand this also using 2 cos A cos B formula, which will be cos A plus B plus cos A minus B. So this term remains, and this becomes cos A plus B term. 2 phi is common, it's taken out. This is cos A minus B term. So I'm expanding using 2 cos A cos B. Okay. Now frequency components are visible clearly. three frequency components are there, which you can identify. Carrier has AC amplitude. This has AM by 2 and AM by 2. And carrier has frequency FC. This has FC plus FM and this has FC minus FM. These three components we can plot and we can see the spectrum of the single tone AM signal like this. Amplitude of the carrier at FC. At FC plus FM, a frequency component with an amplitude of AM by 2. At FC minus FM, the other component, same amplitude, AM by 2. And this is the carrier component. This one is called the carrier component. This one is called the upper side frequency component because it's the component onto the upper side of the carrier. This one is called lower side frequency component. Upper side frequency and lower side frequency components will appear, each having same amplitude. Same could be expanded in exponential form. Right? Each of these cosines I am replacing by e to the power j theta plus e to the power minus j theta upon 2. So this is the carrier represented by these two frequency components now. And here lower side frequency represented by two components, upper side frequency represented by two components, like this. This is same as the previous one, except that we are considering the negative frequency axis as well. Right? Okay. Each component will carry certain amount of power, isn't it? Let's estimate the power carried by each of these frequency components in the modulated signal now. How do we estimate? This is just a sine wave. Just a sine wave having an amplitude of AC. So RMS value will be AC by root 2. Power will be RMS value squared divided by impedance. And this impedance I am assuming as 1 ohm. Okay. I normalized to 1 ohm. Therefore, power can be considered as AC squared upon 2. And similarly, this has amplitude of AM by 2. RMS value will be AM by 2 root 2. And that squared will be the power. So, power will be AM squared upon 8. And AM is mu times AC, modulation index times AC. So, you can write the upper side frequency power as mu squared PC upon 4. PC is the carrier power. This one is identical power, same amplitude. Therefore, lower side frequency power will be this much. Total sideband power is the summation of power carried by this component and the power carried by this component. So let us add the two to find the sideband power. That will be mu squared PC divided by 2 now because I'm adding this portion and this portion. That will be this value. Substitute that value here, you get the total power. Carrier power plus total sideband power will be the total power of the signal. It becomes PC plus mu squared PC upon 2. And PC is common, so 1 plus mu squared upon 2 times PC. This many watts. across a normalized 1 ohm impedance load. Right? So total power is now known in terms of carrier power. Right? So this power balance will be very important because our information is actually carried by the sidebands, these two. Carrier is just there to support it. These two are like the trailer which is having the goods, and this is like the engine of the tractor or engine of the truck. Right? And you can easily calculate the percentage of the power of the carrier with respect to the total power. It will be 1 over 1 plus mu squared by 2, right? From that equation. And if this percentage of the power of the carrier component is too high, we have a problem. And then our power efficiency may be poor because for the real information signal, we are having lower power. For the carrier component, we may having very high power. And that's one issue with the AM. Amplitude modulation has this issue of carrier taking a lot of power of the signal and leaving little bit for the sidebands. Now, this is just an example of we are given a sinusoidal. Now we know how to write the AM signal equation. Here you can see carry amplitude and 2 cos 100t directly added there, xt. And modulation index is half here. And here our carrier is 1600 hertz. Modulating signal is 16 hertz. Just examples with the values, right? This is similar. I leave those examples to you. And our modulation depth could be of different value. For example, the diagram here on screen is showing you what happens when mu is 100%, when mu equals 1. And normally mu multiplied by 100 is known as depth of modulation. Mu is the modulation index. Given as a percentage, we call it depth of modulation. So here, the depth is 100%. How do we know? Then your negative peak will make the minimum point of the waveform to become 0. Envelope will be, minimum envelope voltage will be 0. Here is what happens at different depths. You can notice this is mu is low here. Here mu is equal to 1. You can see the envelope just touching the time axis. If mu happens to be greater than 1, what do we call it? We call it over-modulation. Modulation index more than 1, which is not recommended. Then we have a distortion because our envelope will be, upper envelope will be going like this. Minimum will be below 0. Its mirror image will be like this. It will go above 0. So you have this small portion which is not there in the original waveform. So when you try to recover the original signal, we have a problem here. Therefore, this overmodulation is to be avoided and not recommended. In fact, modulation index could be ideally equal to 1 maximum modulation index mu or m could be ideally equal to 1 or 100% death. Anything higher is theoretically not recommended, but even this modulation index of 1 is not practically used. Typically, modulation index of about 95% is what we normally go as maximum. The reason is due to other imperfections in the modulation circuits and the medium. By the time signal arrives at the demodulator, still overmodulation can happen if mu is equal to 1. The received signal may still be overmodulated. Therefore, it's recommended to keep the modulation index slightly below 1. Okay. And this problem we call sideband splatter problem. If it is present, your signal will interfere to the adjacent channels. Okay, I think let's have a short break here. Oh, this is almost like revision of what you have been doing earlier. I don't think you have much of a problem these parts, right? Shall we have about 10 minutes break and meet again? Okay, we'll meet by 2:25, right? 2:25, we'll meet again.
Recording stopped.
Okay, let us resume. So we discussed about the modulation index, and that multiplied by 100 is the depth of modulation. And then when depth of modulation is more than 100%, we have this sideband splatter problem, which we should avoid. And then what if our modulating signal had more than one frequency component? So far we were studying single tone modulation. If it is a two-tone modulation, right, we may have two frequency components like this with different amplitudes V1, V2. And we can we can use trigonometry to analyze, but it's very easy to extend our argument here that each frequency component present in the modulation will produce that 2 cos A cos B term, which means there will be upper side frequency and a lower side frequency corresponding to this tone. There will be another upper side frequency and a lower side frequency corresponding to this frequency also. So in the spectrum, we will have the carrier, and corresponding to this tone, we will have lower side frequency and upper side frequency like this. Corresponding to this one, if we just extend the argument, we will have Fc minus F2 and Fc plus F2 frequency components with each having amplitude of half the V2, half of mu Vc to mu Vc by 2. Right? Right. So these two, corresponding to this, we have these two side frequencies. Corresponding to this one, we will have these two side frequencies. Power-wise, now earlier we had, now we have two modulation indexes. One modulation index is V1 upon Vc. Vc is the carrier that you can call mu1. Corresponding to this, we will have mu2, which is V2 upon Vc. Now earlier we had this portion as the power. Now we have to add the power of this part and this part, which means this term will come up. So when you simplify this, it will be 1 plus Vc times 1 plus mu1 squared plus mu2 squared upon 2. If you define mu1 plus mu1 squared plus mu2 squared as mu t squared, you can find that mu t is the equivalent or total modulation index. Then your format of the total power will remain. It will be 1 Pc times 1 plus mu t squared upon 2. So same format as earlier. Instead of mu, you can now substitute total mu or equivalent mu to the equation. Bandwidth will now widen because your total occupied bandwidth will be between these two now, which will be 2 times F2. Bandwidth of 2F2, and power equation will be identical. Equivalent modulation index you will have to calculate like this. Supposing I had a third one like this, V3, 3-tone, then you will have equivalent as mu1 squared plus mu2 squared plus mu3 squared. And then the same equation will still hold. You will get two more side frequencies, one on this side and one on this side, and bandwidth will increase to 2F3 now. 2 times F3. Likewise, you can extend your thinking to multi-tone modulation from 2-tone to 3-tone or 4-tone. Likewise, finally, it can go into multi-tone, which is like an actual or practical modulating signal, which is a multi-tone one. So you may have infinite number of tones like this here, filling all these gaps. Each tone producing 2 side frequencies means there will be a large number of side frequencies filling this area, making a band here. Large number of frequencies filling this area, making the mirror image. Now we don't call it upper side frequency because it's large number of frequencies. We call it upper side band now. This one we call lower side band. So in multi-tone AM, we are using the terms USB for upper side band, LSB for the lower side band, because each frequency component present in your baseband signal will produce 2 side frequency component of equal amplitude around the carrier. Hope it is clear. This part I already explained. So equivalent mu, some books might write it as mu equivalent. I'm writing it as total mu. And this is extendable. In multi-tone, you can say mu equivalent will be mu1 squared, mu2 squared, likewise. Same number of tones. Total power will be carrier power plus 1 plus that equivalent mu squared upon 2. Okay. Like that, right? So total sideband power will be mu total squared PC upon 2. PC means amplitude of the carrier squared upon 2. Total power given by that. So when you transmit multi-tone AM signal, your total power is being contributed by the carrier and the sidebands. Right? Carrier is having major portion, sideband power is somewhat less in AM, and higher the modulation index, if mu is higher, sideband power to carrier power ratio will increase. Or sideband power to total power ratio will increase, which is a good sign, right? Because when you are transmitting a certain signal, if that signal major portion of the power is carrying the actual information signal, which is the sideband part, then it is better. That's why in a AM signal, a higher modulation index is desirable. However, it should not overmodulate. One question Ratnak is asking, when we have a band, how do we find mu? We find mu like this. This is the formula. For each modulating signal frequency component, you will have individual mu values. So all such mu values will have to be squared, added, and taken the square root. That will be the equivalent mu. However, when you take a signal like music, for example, music signal will have infinite frequencies in this area. So I think your question is, how am I going to add infinite number of these, right? Which is not practically possible. So far we are discussing discrete multitones like this. However, if we have multitones infinite number, then we have to have a different strategy in designing the defining the modulation index. Right? So at the moment, don't worry about it because we are assuming multitone, each tone with discrete mu value. Now we will try to generalize, which will answer your question, because so far we did not discuss the generalized or practical modulating signals. Initially, we started with the single tone. Then we extended our thinking to two-tone modulation, then three-tone. Likewise, now we know the theory of a multi-tone modulating signal or multi-tone AM signal, right? Now let us try to generalize this for a practical modulating signal, which could be a signal like this, as you see in the screen. A signal coming out from a microphone when you amplify will be like this, right? We'll have positives, negatives, and we'll have variations. So it is not a single tone now. Therefore, your xt will be now a waveform xt, and peak value of that waveform we will define as AP, right? Remember earlier we were using AM for the amplitude of that single tone you modulated. This is not a single tone. This is the peak value of the whole waveform. In this case, this amplitude. This amplitude maximum value is AP. So you write your xt in terms of a waveform now with a peak value of AP. Now this will answer your modulation index question, right? So that's the modulating signal. We keep the peak value here, and xt is the waveform having amplitudes between -1 and +1. So it is a normalized waveform. It's normalized with respect to the peak value AP. Okay. Now after modulation, now what is the envelope? You are adding this part to the original amplitude AC. Now I will call it envelope, E for the envelope, right? This is the envelope equation. Then take out the AC from the envelope. It will be 1 plus AP upon AC times XT. That is what we call mu here. Mu is AP upon AC. Sorry. Sorry, I could not resume the recording.
Recording in progress.
Okay, so when generalized, we will have a modulation index defined this way. Right? So this is the answer to the question you asked. How do we define modulation index for a practical signal like this? Right? It is with respect to the peak value of the waveform. So that divided by the amplitude of the carrier is the definition of modulation index for such a waveform. Still, I'm using the same notation, mu, for that. So our modulated signal will be that envelope we got into the cosine part, sinusoidal part, cos omega ct, and let us substitute for envelope. Envelope is given by this. That is the AM signal waveform. Now, when you look at, this is the mathematical expression for the generalized AM signal. Now it is not single tone. It is having infinite number of tones, and it is a practical modulating signal waveform. When you look at the time domain of the modulated signal, it will be like this upper waveform. Modulating signal, the baseband signal, is the lower waveform on the screen. Of course, there are lots of oscillations here. So you only see the envelope clearly. So that's how the envelope will look like when you modulate your audio signals, video signals, etc. on a carrier. Mathematically, this is the equation for this modulated signal. It's a generalized AM signal, right? And that also we can analyze the same way we did earlier for the single tone signal. Expand by multiplying, by removing the brackets, and then find the spectrum. Now this one is the carrier, clearly, carrier frequency, and this one we will have to transform into the Fourier, take the Fourier transform, and it's a product of xt into cos omega ct. This is sidebands, and this sideband part carry the real information. This one is only the carrier frequency. In that, you have no information in this component. This component carries our information signal. Okay, let us look at the frequency domain here. Before that, if you have to make a modulator, functional diagram will be like this. First, you take xt signal, this portion, multiply that xt with AC cos omega ct using a multiplier. This one can be simulated by a multiplier, and then you need an adder for this. You add it with the carrier. So functional block diagram will be taking xt and giving a scale factor of mu, then multiplying with the carrier. So that is this multiplier. Then adding this component AC cos omega ct to that again, and that will be the AM signal. So functional block diagram will be this for the AM modulator. Over modulation I already mentioned. Right? Now we will look at the frequency spectrum. Because we have a multiplier here, xt is being multiplied with cos omega ct. In the frequency domain, xt I will write as xf. And this one in frequency domain, we already studied at the start. It's only the carrier component. This one is the spectrum of xt signal, which is xf, shifted in the frequency domain with an amount fc, shifted to the upper side as well as to the lower side. So we have the carrier plus lower side frequency component here. We call it LSB. Upper side frequency part here, which we call USB. When plotted, upper side band will look like this. Lower side band will look like this. Carrier will be at the center. So you get two side bands. Okay. Carrier component given by this. And these are the side bands. Modulating signal spectrum, I will assume like this. And after modulation, you will get this kind of a spectrum. Two carrier components like that. And this one, this term, will produce these two. This term will produce these two. Bandwidth will become 2 times the bandwidth of the baseband signal. In the spectrum analyzer, when you view it, you will get this kind of a graph. This is frequency axis. Time domain, I already showed you. This is modulating signal. This is modulated signal in time domain. This is modulated signal in the frequency domain, where you can see the carrier at the center here. And this portion is the upper side band. This portion is the lower side band. Spectrum analyzer will give you a picture like that. Then in the generalized AM signal, shall we do the power calculations and see? This is the general AM signal equation. And when you square it, for the power, you need to square the voltage, assuming 1 ohm generalized load resistor. So I'm not writing the resistance value. Instead, I'm just taking V squared here. So square this, you will get cos squared T. Cos squared theta, you are replacing with half 1 plus 2 theta. That is this portion. Then multiply separate into individual components like this. Okay, and then find the average value of the squared waveform. And because you have cos 2 omega ct here, when you average out, it will not make a value, so it will become 0. Average value means you integrate over a period and divide by the period. So if this waveform is integrated over a period and divided by the period, I will use this notation for that. This is for the average value. Substitute and integrate. You will get average value of this portion multiplied by AC squared by 2. Then average value of this portion, I'm using this symbol for the average value. Average value of this portion multiplied by AC squared upon 2. And because of cos 2 omega ct, its average becomes 0. So this term will vanish. And we need to find the average value of this. This will also average to 0 because we are assuming that xt is a waveform having average of 0, equal plus and minus signs like a typical audio waveform or typical video waveform, right? So that term will also vanish. So when those terms are 0, it simplifies to this. AC squared by 2 multiplied by the average value of 1 plus mu squared x squared t. And mu squared x squared AC squared by 2 will be the value. Then here it will be the average value of only x squared t. This is the carrier power. And this is modulating signal power. Let us call it Px, power of the signal x. And then this simplifies to Pc plus mu squared Pc into Px. This is also Pc. Now that will be the total sideband power. I'm going to call it PSB, total sideband power. This is the carrier component power. So overall, it will become 1 plus mu squared Px multiplied by Pc. And each sideband have equal power, has equal power. Therefore, it's this sideband power divided by 2 that you have in individual sideband. This is total sideband power. Individual sideband will have 50% of that. Now that ratio, carrier power as a ratio of the total power of the signal will be given by that. And since mu into xt is less than 1, mu squared px is a value less than 1. Which means at least the maximum this can take is 1, which means it's 1 over 2, the maximum. What does that mean? At least 50% of the total transmitted power of your AM transmitter will be residing in the carrier term. And that is independent of our xt. And that 50% conveys no information, right? It's only the carrier. So that's a bit inefficient. It's like you have a vehicle which has a large portion of the vehicle taken by the engine compartment and only 1 or 2 seats for the passengers or the goods. So space available for the goods is much less, but the engine and the vehicle itself will be very large, very big. That's a poor design for transportation. So we have such a system in AM here, right? At least minimum of half, but it will be more than 50% taken by the carrier. Right? So power efficiency is defined as power of the useful signal divided by the total power. The actual useful power for the after demodulation will be only one sideband. We don't need both sideband also because one is a duplicate of the other or the mirror image of the other. Therefore, if you take the power of one sideband, that is a useful power. Divide that by the total power, you get the power efficiency given by this equation. So what is the highest power efficiency you can get? That is when mu squared px takes its largest value, which is 1. And that means useful power efficiency will be less than 0.25. Less than 0.25. So it's very poor, right? Only 25% or less of the transmitted power will be actually being used by your information content. So it's a very kind of a large vehicle carrying small amount of goods, right? Small amount of information. Hope this is clear, right? This shows kind of a weakness in AM. Power efficiency with respect to the different frequency components of the transmitted signal, that power efficiency is not very good. Then the question, why use AM if it is so poor in power efficiency? One main reason is its demodulator is so simple and very low cost, and that's known as an envelope detector. And that means the receivers could be made at low cost. However, transmit-wise, it will be highly inefficient in power transmission. You need very high power. So in a situation like broadcasting, what do you think? There will be one main broadcast transmitter operated by operator, and there will be large number, thousands or 10,000s or even more receivers, individual users. So if the individual users' equipment could be more simple and low cost, broadcasting wise, it's beneficial. Therefore, this was originally used for such purposes. This is the demodulator, which is a very simple circuit. Only 3 components, diode, capacitor, and a resistor. Known as envelope detector because envelope is where our information is. You are going to detect that part only. So when you apply, this portion is like a half-wave rectifier, and this portion is like a low-pass filter. And the signal which is coming in here is our AM signal which envelope like this. And diode will rectify 1/2 so that you will have that envelope here. After that, capacitor will keep the peak values like this. Capacitor will try to follow the peaks of the rectified waveform this way. This half is rectified by the diode anyway. This part is not there, lower half. Capacitor will be charged, and during these interpulse gaps, it will be discharged and refilled to the top of the next pulse. Likewise, the envelope will be followed by the capacitor voltage and envelope will be recovered. However, your selection of R and C values are very critical, because if capacity is not sufficient, it will discharge heavily between pulses like this, distorting. And if the capacity is too much, then it will have a problem like this. Right? You may miss these peaks. Capacitor will discharge this way. So selection of the capacitance is done according to this rule. Time constant is very carefully selected to handle frequencies present in the waveform baseband signal. Okay. So our demodulation is then, this one is what we call envelope detector, which is one of the most simple demodulators. However, there is a more generalized demodulation technique available for modulation, which is called coherent detection. This envelope detector does not belong to that coherent detection theory. What is coherent detection? That is also possible to be applied to the AM signal to demodulate. What do we mean by coherent detection or coherent demodulation? This is that principle. You multiply your incoming modulated signal with the carrier portion of the carrier. Multiply will be followed by a filter. This is the AM signal. Multiply with a portion of the recovered carrier, and resulting signal is low pass filtered to or get the original baseband waveform. This will work on AM also. However, if you have to implement this principle, it will be circuit will be more complicated. Therefore, coherent detection is not popular for AM demodulation, although it is possible to use. Coherent demodulation principle is possible to use on AM, however, not popular because envelope detector is more simple and get the job done at a very low cost. This is the demodulation principle. First, the multiplication. Demodulation is first this multiplier. Okay. Just multiply these two. This is the modulated signal. This is the carrier. Multiply the two. You get this answer. Right? And then cos squared you replace by 1 plus cos 2 omega ct, like this. 1 plus cos 2 omega ct, and expand that. Sorry. And when you pass it through the low pass filter, this cos 2 omega ct component will be knocked off, will be filtered out, and you will get this portion, which will have your xt, original xt is there along with some DC portion here. So you may need to block the DC by using a capacitor kind of thing and take out the AC component. That will be demodulated waveform. As I said, this is possible to use, but practically not used because envelope detector is there. Then why do we discuss this? Because this coherent demodulation principle, this principle we can use for many modulated signals for demodulation. So it's a very generalized principle being used in digital demodulation techniques and everywhere. So that is why we discuss the principle. What is the principle? We multiply the incoming signal with the carrier or portion of the carrier, and then low pass filter the output. That way, that idea we call coherent demodulation or coherent detection. Why the name coherent? Because this carrier that you are applying here should be same carrier or portion of the same carrier that you used for modulation also. This part, this component is in the modulator. This is in the demodulator. Should be the same carrier, same frequency. That is why the name coherent, because it's synchronized. Has to be synchronized with the carrier at the transmitter. Okay, so you can make a very simple receiver like this. From the antenna, amplify the incoming signal, then multiply with the local oscillator so that you recover the audio directly. This is without using an envelope detector here. This block diagram is showing you the coherent detection principle being applied. So your audio will come out directly now, and that you can amplify. Although I'm using audio, this could be a video signal also, right? Now this idea we call heterodyne receiver. Heterodyne receiver. What is the idea? Incoming modulated signal multiplied with the locally generated coherent oscillator so that output is directly becoming the demodulated audio. And how do we tune from one channel to another? We need to tune the RF filter here using a capacitor, and local oscillator also should be tuned simultaneously, which means that we are taking a capacitor, one half is used here, other half is used here, and we gang couple them. Gang couple means same control is used by the, assume that it's a rotary knob, for example. Same rotary knob will simultaneously tune both portions of the capacitor so that when carrier frequency is tuned to a different channel, your local oscillator frequency also tunes parallelly, keeping their difference between the local oscillator frequency and the carrier frequency being equal to your information signal frequency or demodulated information signal. So that's the heterodyne receiver principle. However, this was used in a very old days, did not become that popular because it had adjacent channel interference issue because of these filters. Right? And the bandwidth was wide, too wide. When you tune from one channel to another, it will also pass a portion of the adjacent channel along with your signal. Therefore, the sound or demodulated output is getting interference from the adjacent channels. That's why heterodyne receiver is not that's suitable for practical use. But we have an improved one called super heterodyne, which we will look at next time. And even more improved one, which is called double super heterodyne receiver. Those are actually based on the heterodyne principle. However, they have been improved to overcome this interference issue. Okay, so today we will stop somewhere there. In summary, what we discussed is basically kind of a revision from previous semester on modulation. So we just revised
kind
what
of a
is
revision,
modulation.
though.
And then we were able to divide the modulation into multiple types, and we took AM for discussion. And under AM, we were able to discuss single tone AM, two tone AM, and then multi-tone AM. And that led to generalized AM signal analysis, where we were analyzing the spectra. And also we were analyzing the power distribution among different frequency components in a generalized AM signal. And we found this huge imbalance between carrier and the sidebands with respect to power, which is one weakness. And then we looked at the demodulation techniques, and we are halfway there. Next time we will look at the other receiving principles for the M radius. Okay, so thank you very much for participation, and we will meet next Wednesday, right? So although I am on leave, I will have to do a few lectures for you. Maybe first 3 to 4 weeks I will be taking. Right? Thank you very much.